everyone, I'm Mr. Pinola, and today I'm representing the motion of an electron. An electron is a negative charge, and as we learned from our most recent unit, electrons can move. Right now, I'm moving in a circle around this desk, and so if I'm an electron that is moving in a circle, or just moving in any path, I am representing electric current. And that's going to be the focus of our video today. Electric current, which is the flow of electrons. So let's get that definition settled before we move forward here. Our word is electric current. And perhaps you've heard of it before. It is the flow of electrons. It's important that we say this is electrons that are flowing and not protons. Remember, electrons are free to move, whereas the protons are very tightly bound and they stay where they are. That's why in charging by friction, charging by contact, and charging by induction, it was always the electrons that were moving from one object to another, never the protons. Also, it's important to note the word flow. Flow implies that it's moving from one place to another. The electrons are moving almost like water molecules in a river. They're moving from one place to another. Me? I was moving in a circle. I was flowing in a circle around the table. So I was an electron that was flowing in a circle, meaning that I was representing electric current. But in reality, when you have actual things through which electrons flow, such as wires, you would have many, many, many electrons that would all be flowing at the same time. Let's take a closer look now at the two different types of electric current that you might encounter. The motion that I was doing earlier, just moving in one direction around the desk, represents a specific type of electric current. This is called direct current. Do you know why it's called direct current? That's because it's only moving in one direction. However, sometimes electrons in a circuit do some interesting things. For example, watch the motion of an electron, me, emulating another type of current. Here we go. Did you notice what happened there? I flipped my direction a couple of times. So I was moving in one direction, and then I switched to moving the other direction, and then I switched back. I was changing or alternating the direction of my electric current. This is appropriately called alternating current. So the two main types of current that you are going to be dealing with throughout this unit are direct current, in which the electrons only flow one direction, and alternating current, in which the electrons constantly change which direction they're moving in. They flip back and forth. So let's summarize what we just saw. Direct current which is sometimes abbreviated as DC, is current that flows in one direction. When I was moving in a circle and not switching my direction around the desk, I was following direct current. Now, alternating current is something different, so let's define that as well. Alternating current, which is sometimes known as AC, is current. That constantly switches its direction. That means if you have alternating current, the current is constantly flipping back and forth. These two types of current, DC and AC, are the two main types of current that exist in the world today. So now let's take a look at direct and alternating current in a circuit. Here on the screen in front of you, you see electrons that are moving through a circuit. These electrons are flowing only in one direction. They represent direct current. Notice what's causing the electrons to move in this way. It's a battery. Batteries are sources of direct current. Current can only flow one way if it's a battery that is driving the current through the circuit. Now, if I were to remove the battery and replace it with a source of AC voltage, and I connect my circuit because I need a complete path for the electrons to flow, watch what happens now. Notice my electrons shift. They constantly switch directions back and forth. This is alternating current. Do you know what provides alternating current? Well, you might look at this and say, why would somebody ever use alternating current? Because it turns the light on and off. But actually, almost all the outlets in your house use alternating current. The fact is, though, that they alternate so fast that the lights are technically blinking real fast, but you can't even notice it because the current is switching back and forth so many times. Remember frequency? If an electric circuit has a frequency of 60 hertz, it means in 1 second, the current is flipping back and forth 60 times. So fast that it's barely noticeable to the human eye. So, alternating current means that the current constantly is switching its direction, and that is the current that comes from the outlets in your home, unlike direct current, which came from batteries. Let's take a look at one last thing about current before we move on to another topic. Here is a battery. This is specifically a C battery. You will notice that every battery has two different ends. One end has a little bit of a bump on it, and that's how you can tell them apart. The part that has a bump is the positive end of the battery. Here's our negative end, and here is our positive end. So now let's go back to our circuit that we had in the simulation and take a look at which direction the current is flowing, bearing in mind the negative and positive end of the battery. Remember, the positive end of the battery is the side that has the bump, at least when we're talking about a battery like this, and the negative end of the battery doesn't. Usually, if you're using a battery in the lab, that will be labeled for you. So welcome back to our circuit construction kit. Here, we have a battery. And so if I disconnect the battery for a moment, you will notice that it has the two ends that I spoke about earlier. Here's the side of the battery that has the little bump on it. It's the positive end of the battery. Here's the other end of the battery that does not. That is the negative end of the battery. If I put this battery in the circuit, watch the way the electrons flow. The electrons are flowing from the negative end of the battery towards the positive end of the battery. This is called electron flow because the electrons, as we might expect, are moving away from the negative end. They want to repel the negative end of the battery, and they are moving through the circuit towards the positive end of the battery. They can then get recharged by the battery, and they continue to pass on through. So this is what electrons actually do. They flow from negative to positive, and that is called electron flow, and is in reality the way that electric current moves. But now take a look at this circuit. Do you see that the arrows are flowing the opposite direction? Here, the arrows are showing particles moving from the positive end of the battery to the negative end of the battery. That seems wrong. Electrons don't move away from positive, and they certainly don't move towards negative. This definitely doesn't seem like the way electrons would flow. However, if we look over at the label on the right, this is still a type of current. However, it is called conventional current. When Ben Franklin was first writing books on electricity, he assumed that it was the protons and not the electrons that were moving. Protons would move from positive to negative, just like you see the red arrows doing, leaving the positive end of the battery and coming back at the negative end of the battery. Franklin published a lot of his research, but scientists years later discovered that no, he was wrong. It wasn't the protons that move, it was the electrons. So even though we know it's technically the electrons, like this, we still have Ben Franklin's terminology from when he thought the protons are moving. And that's why when you hear a scientist refer to conventional current, they are talking about the direction that protons would move. Conventional current flows from positive to negative, unlike electron flow, which flows from negative to positive. Two different types of current. Electron flow is the real kind of current, but conventional current is a term that many scientists use, and you may have to as well. So let's take a look at those two types of current that we just spoke about. If you have current moving in one direction, that current can either be electron flow, meaning the movement of electrons that moves from negative to positive, or it can be conventional current, which is just the exact opposite. This doesn't happen in real life, but scientists show current sometimes on paper moving from positive to negative, which would be conventional current. I know it's strange and we'll talk about it during class, but conventional current flows from positive to negative because it represents the potential flow of protons. So let's stick with electron flow for now, because we know that that's actually the way the current flows. It's conventional current, we just have to flip that thinking in our head. However, I'm going to take this piece of wire and delete it. I now want to see which kinds of materials will allow the electrons to actually flow through them. We know wires can do just fine. Current can flow through the wires, no problem. Wires are thus considered good electrical conductors. But what else is a good electrical conductor? Well, let's take a look at our list on the side. I'm going to scroll down and I'm going to pull out a paper clip. If we put this paper clip in the circuit, is it an electrical conductor? You bet it is, because the paper clip allows current to flow through it. But how about a dollar bill? Is the dollar bill an electrical conductor? No, it's not letting any current flow through it. This dollar bill would be considered an electrical insulator. It has stopped the flow of current, and now nothing can get through the circuit, and the light bulb is not lit. The dollar bill is a bad electrical conductor, and therefore a good electrical insulator, unlike the paper clip, which, largely because it was made out of metal, is a good electrical conductor, and thus a bad electrical insulator. It allows current to flow. So let's summarize what we found about electrical conductors and electrical insulators. Electrical conductors, like the paper clip in our simulation, are materials which allow electrons to flow easily. Electrical conductors are materials which allow electrons to flow easily. That means if I put something in a circuit that's an electrical conductor, usually the electricity will flow very easily. It will be able to pass through. Most electrical conductors are metals. Sometimes human skin can even be an electrical conductor. In fact, if you touch high voltage power lines, electrical current will move through your body and your skin will be an electrical conductor. Did you know that if your skin is wet, it makes your skin an even better electrical conductor? We'll talk more about that later on in our unit. But for now, you should know that your skin and most metals are very good electrical conductors. Copper is especially good, and that's why most wires are made out of copper. However, electrical insulators are different. Electrical insulators are materials which do not allow electrons to flow. Notice when I put the dollar bill inside the circuit, it stopped the electrons from moving. That's because the dollar bill was a great electrical insulator. It did not allow current to pass through. You may have noticed that I just said that wires in a circuit are made out of copper. But you might be thinking, wait, aren't a lot of wires coated in rubber? And it's true. A lot of wires are copper on the inside, but they're coated in rubber. And that's because if you touch a wire, you don't want electrons flowing into your body. And so a wire would need a good electrical insulator on the outside so current doesn't flow into anything else. So some examples of good electrical insulators are rubber or plastic or wood. These are things that would not allow electricity to easily flow. In fact, did you know that air is also considered a good electrical insulator? That's why usually electricity does not flow through air, unless we have static discharge and a sudden pathway appears through the air for the electrons to escape. But for the most part, these objects, just like my dollar bill in the simulation, are very good electrical insulators. Conductors allow the flow of electricity. Insulators prevent the flow of electricity. So I hope you learned something today about electric current. Let's wrap up with one last thing about electric current. I'll write it on the board again. Sometimes we're going to be asked to use electric current in equations to do calculations. And when we do, we will give a symbol to electric current. We're going to give it the symbol I. Now, I know that doesn't make a lot of sense, but you've got to make that connection in your head. The symbol I represents electric current. We also have to give electric current a unit. And the unit that we measure electric current in, just like we might measure distance in meters or time in seconds, is amperes. Now, amperes is named after a French scientist whose last name was Ampere. However, we often shorten that word to amps. Have you ever heard of an amplifier for an electric guitar? Notice the connection between the electricity that is flowing through the amplifier and our current, which is of the electric variety. We sometimes represent amps just with the letter A. And remember, that is our SI unit. There could be other units for current, but this is the unit that we as scientists will choose to use. So, if I was writing this out for an equation, I could write that the current I through a wire is equal to 3 amps. Notice I'm not writing A equals 3. I'm not writing I equals 3 without a unit. I'm not writing 3I. I'm writing I, which represents the current. That's the symbol for it, is equal to 3 amps. Amps is our SI unit. To summarize, we spoke about a lot of things today. We started off by learning that electric current is the flow of electrons, usually through wires, and that there can be two types of electric current. It can be direct current, in which the electrons are moving only in one direction, or it could be alternating current, in which the electrons are constantly switching the direction they're going. Direct current is current that is supplied by batteries that can only go one way, whereas alternating current is actually supplied by the outlets in your house or at your school. And that's because the electrons constantly flip back and forth. But they do that so quickly that we don't actually notice the lights flickering on and off in our minds. We also talked about the fact that current is represented as electron flow, meaning that current travels from negative to positive, because every battery has a negative and a positive terminal. But Ben Franklin made a mistake one time and thought that it was the protons that actually moved. So he said conventional current moves from positive to negative. And we have to know that term as well. Conventional current is positive to negative current. Electron flow is negative to positive. Lastly, we wrapped up by talking about types of materials that would allow current to flow or not. Electrical conductors, like many metals, are great electrical conductors. We can put them in circuits and they will allow the current to flow through them. But many materials such as wood, rubber, and plastic are electrical insulators and do not allow current to flow through them. If I was to stick a piece of wood inside an electrical circuit, it would shut the whole circuit down because no electrons would be able to pass through the wood. I hope you learned something today about electrical current from our video, and we're going to take a look in the next couple of videos at a couple of factors that affect how big or how small the electrical current flowing through a wire can be. Thanks for watching.